Polynomials. What comes to your mind when you think of the word polynomial? Polynomials. It is made up of two words, poly and mials. So, poly stands for many and mials many terms. So, polynomial is nothing but an algebraic expression with many terms, but of course written in a proper order. There are certain conditions to be followed. So, what will we learn in this chapter? We'll learn how to define a polynomial and its basic terminology, identifying the zeros of a polynomial and its graphical study. Meaning of a polynomial, as I told you and as you can see on the board, a polynomial is an algebraic expression. What is an algebraic expression? Let's recall. An algebraic expression is an expression or a statement in mathematics combining some variables and constants, and these variables and constants are combined using the four mathematical operations of addition, subtraction, multiplication and division. So, a polynomial is an algebraic expression consisting of multiple terms. But what is so special about the arrangement of these terms? Whenever we write a polynomial, it is always written in decreasing power of x, and the highest power determines the degree of the polynomial. So, coming to the first term, coefficients. Coefficients are the numericals which are multiplied with the variables. So, the real numbers that precedes the variable, precedes means just before the variable, that is multiplied with the variable, they are called the coefficients of the polynomial. Variables are the numbers which are multiplied with the coefficients or the letters of the English alphabet whose values are not known, whose values are not constant. Degree of a polynomial, as I told you, any polynomial is written in decreasing power of the variable, and among all the variables or among all the terms in a polynomial, if we have to determine the degree, we have to look at the highest power of the variable. The highest power of the variable determines the degree of the polynomial. As we can see in this example, here the highest power of x is 3. So, the degree of the polynomial is 3. Coming to types of polynomials. Of course, if the degrees are different, the polynomials will be of different nature. The first is a linear polynomial. As the name suggests, if we graphically represent this polynomial, it will give me a straight line. And a linear polynomial is one in which the highest degree of the variable is 1. In a quadratic polynomial, the highest degree is 2 and it is a quadratic polynomial. So, a quadratic polynomial is a polynomial of degree 2. A linear polynomial is a polynomial of degree 1. A cubic polynomial likewise is a polynomial of degree 3. Now, starting with linear polynomial, we have before us Px. Px is a function in x, a polynomial in x equal to 4x plus 8. As I told you, we write down the polynomial in decreasing power of x, the highest power being 1. And what gives rise to this constant term in a polynomial? After x raised to the power 1, we'll have x raised to the power 0, and we know x raised to the power 0 is 1. That is why we do not write a variable with the next term, and this gives rise to a constant term in the polynomial. So, here the highest power of the polynomial is 1, which means it is a linear polynomial, and from here we come to the general form of a linear polynomial. If it is a linear polynomial, obviously it will have its first term as a coefficient of x and the second term is a constant term. The first term will always be multiplied with x because x raised to the power 1 is the variable with the highest power. So, the general form is ax plus b. Looking at a quadratic polynomial, the highest degree of the variable is 2, the second highest 1 and the third is 0. But it is not necessary that every time a quadratic polynomial will have 3 terms. It may have 2 terms also. I could have x square plus 3 also. And that is possible only when the coefficient is 0. So, when I am saying that the variables are arranged in decreasing power, it is not necessary that each and every power of the variable will be visible. Here, the middle term could become 0 in case the coefficient of x is 0. But the general form of writing a quadratic polynomial is ax square plus bx plus c, the first term having power 2 of x, the second term having power 1 of x and the third term having power 0 of. Looking at the cubic polynomial, it is a cubic polynomial because the highest power of the variable is 3. It is a polynomial of degree 3 and the general form is ax cube plus bx square plus cx plus d. Again, we can see that the power of x is written in decreasing order starting from the highest to the constant term, which is of the power of the variable is 0 there. Now, what do we mean by zeros of the polynomial? Suppose we have a polynomial px equal to x square minus 4x plus 3. So, when I am talking about the zeros of the polynomial, I am talking about that value of x which will make this expression equal to 0. And how do we find it? Suppose I put x equal to 1. This is just by a trial method. Putting x equal to 1, I can see 1 square minus 4 into 1 plus 3 will give me 0. Even if I put x equal to minus 1, let us see whether I am getting a 0 or not. No. Putting x equal to minus 1, I will get p of minus 1 is equal to 8. But we cannot use the trial and error method every time. For finding the zeros of the polynomial, we need to factorize the polynomial. So, the value of a polynomial px when x is equal to k, where k is any real number, is the value obtained by substituting x as k. The 0 of the polynomial is defined as any real value of x for which the value of the polynomial becomes 0. When this expression becomes 0, that particular value of x for which this expression becomes 0 is the 0 of the polynomial. Coming to the geometrical interpretation of the polynomial. Starting with a linear polynomial, we start with a linear polynomial of the form ax plus b, and here the example is 2x plus 3. Plotting this on a graph paper, first we construct a table in x and y. Putting the value of x as minus 3, I get the value of y as 2. Putting the value of x as minus 3 upon 2, I will get y as 0, and connecting all these points, I will get a straight line. So, the point where the graph intersects the x-axis, I can see it intersects the x-axis at minus 3 upon 2, comma 0. It intersects the x-axis at the point where the value of x is minus 3 upon 2. And we know putting x equal to minus 3 upon 2 has given y equal to 0, and y is nothing but my linear polynomial. So, clearly from the graph, that value of x which will make y equal to 0, or a point on the x-axis intersected by the graph, will give me the 0 of the polynomial. So, 0 of any polynomial graphically is that point where the curve or the line intersects the x-axis. So, the line intersects the x-axis at -3 upon 2 comma 0, and the 0 of the polynomial is hence x is equal to -3 upon 2, the point on the x-axis. So, geometrically the 0 of the polynomial is the x coordinate of the point where the graph intersects the x-axis. If the polynomial px intersects the x-axis at k comma 0, any point k, then this k is the 0 of the polynomial. The graph of a linear polynomial intersects the x-axis at maximum of one point. So, if I consider any line, be it like this, a positively sloped line or a negatively sloped line, always a linear polynomial or a straight line will intersect the x-axis only at one point. Coming to the quadratic polynomial. A quadratic polynomial will give rise to a U-shaped curve known as parabola, and the parabola can intersect the x-axis maximum at 2 points, and these 2 points can be equal in case the parabola passes through one point only, that I will show you in the diagram. Here in this case the parabola intersects the x-axis at two distinct points, which means there are two distinct zeros of the polynomial. So, if I consider y is equal to x square minus 4x plus 3 and I make a table and draw a graph, I will get a parabola. Why do we get a parabola? Because for two different values of x, I will get the same value of y. As I can see here, for x equal to 1 I get y equal to minus 6, and for x equal to 2 also I am getting y equal to minus 6, and after that to the left and to the right the values are symmetrical. So, it is giving rise to a symmetrical curve. It is giving rise to a symmetrical curve, and the axis of symmetry is lying between these 2 points. So, here the axis of symmetry is lying between the points 1 and 2 on the x-axis, and on either side of the graph the parabola is symmetrical. That means for two different values of x, for x equal to 0 and for x equal to 4 also I am getting, for x equal to minus 1 and x equal to 4 I am getting y equal to 0, for x equal to minus 2 and 5 I am getting x equal to y equal to 6. So, I will get two distinct points every time for the same value of y for two different values of x, which give rise to this parabola. Now, coming to the point of intersection, we can clearly see that the parabola intersects the x-axis at 2 points, two distinct points, which means that there are two zeros of the polynomials which are distinct and real. Looking at this polynomial, this is a cubic polynomial, and since it is a cubic polynomial, I can see that the graph intersects the x-axis at 3 points. I am talking about x-axis, not y-axis. This point will not be considered because this point is not lying on the x-axis. The graph is intersecting the y-axis. We only have to take the x-axis, the point of intersection on the x-axis. After drawing a table, we will get an S-shaped curve always for a cubic polynomial. And here we have the comparison between the two. Here the graph cuts the x-axis at 2 points and we have a quadratic polynomial, and here we have a cubic polynomial intersecting the x-axis at 3 points, giving rise to 3 zeros, minus 1, plus 1, and the shape of the parabola of a quadratic polynomial depends on whether the value of a is positive or negative. In the polynomial, if the value of a is positive, it will be an upward rising parabola, and if a is negative, then it is a downwards falling parabola, inverted U form of. The parabola open upwards if the value of a is positive, and it opens downwards when the value of a is negative. Now let us see what we have learned so far here. The x coordinate of the point where the graph of the polynomial intersects with the x axis is called the 0 of the polynomial. Very important point we have seen. Then when it was a linear polynomial, the graph intersects, so the line intersects the x axis at one point. So degree 1, so the point of intersection is 1. When the degree is 2, we get a parabola, and the parabola intersects the x axis at 2 points. So when the degree is 2, there are 2 zeros. When the degree is 3, there are 3 zeros. We have seen in a cubic polynomial also, a cubic curve. So if I talk about the nth degree, so the nth degree polynomial will intersect the graph at n different points, and it will have n zeros, a maximum of n zeros. I will not say exactly n zeros, because talking about a line may not intersect the x axis at all. It may be a line parallel to x axis. So that can be a case. So the maximum number of zeros is determined by the degree. It is not exact, but maximum number. Similarly, if I am talking about a parabola may touch the x axis at one point. The minimum point of the parabola may lie on the x axis. In that case also, we will have only 1 zero, but maximum we can have 2. So the nth degree of a polynomial determines the maximum zeros of the polynomial. The shape of the graph of a quadratic polynomial is called a parabola. The shape of the parabola of a quadratic polynomial depends on the value of a. If a is positive, we will have upward opening parabola, and if a is negative, we will have a downward opening parabola.
To watch the complete video, download the Upbind educational app from Play Store and App Store.